Hello everyone, so welcome to College Algebra Lecture 11, and this is on section 3.7 in your textbook on inverse functions. So let me give the definition of an inverse function first. So for any one-to-one, and this is important, it has to be a one-to-one function, let's say f of x equals y. A function f inverse, and the inverse is written as a -1, sort of as the exponent of x, is an inverse function of f if f inverse of y gives you back x. Okay, so think about what's happening here, right? In this first, for the regular function, x is my input, y is my output. For the inverse, it takes the original output and gives you back the input, right? So think of an inverse function as sort of like undoing the original function, okay? Now, because it has that property, the following is true. If I take the inverse of the original function, so if I do a composition where I have f inverse of f of x, that's going to give me back the input x. It gives me back the argument x. And vice versa. If I apply the function of the inverse, so if I do a composition again of x, I also get back the original input x, right? So it like undoes what the original function did. Another way of saying it, so inverse function will undo the original function. So, for example, if f of a is equal to b, so now my input is a, my output is b, then if I do f inverse of b, what do I get back? I'm going to get back a. Right? So f of a equals b, then f inverse of b becomes a. So the inputs and outputs switch. So for example, let's assume that the function f is one-to-one. Okay, so we know it has an inverse. So if we're told if f of 6 is equal to 7, then we want to find f inverse of 7. Well, if the input to the original function is 6 and the output is 7, if I take the inverse function of the output, right, of 7, I should get back the original input. So this should be equal to 6. Okay? And it doesn't matter which way you go, so I could start it with the inverse. I could say if f inverse of -6 is -4, and I want to find the original function of -4, that's going to be equal to -6. Right? The inputs and outputs flip-flop, they switch. Okay, here's another example. Let's say I'm given this graph, right? So this linear graph, and I want to do several things. I want to find f of 0. I want to find f inverse of 0. Then I want to solve f of x is equal to 0 for x. And then finally, I want to solve f inverse of x is equal to 0 for x. Okay, so let's start with f of 0. So this is the input is the x-axis. The output is f of x, or you can call it y if you want. So if I want f of 0, it's saying my input is 0. What's the output? Well, in this case, if I go up to the graph, it's 2, right? So f of 0 is simply equal to 2. So this is 2. What about f inverse of 0? So now I kind of have to reverse, right? I have to reverse my thinking. This 0 is the output, right? The output is 0, the y is 0. So what is the input such that the output is 0? It's got to be 3, right? If the input were 3, the output would be 0. So therefore, if I do the inverse of 0, that's got to give me 3. Okay, another way to think about it is think about it in terms of the functional form, right? If I reverse this means that f of 3 gives me 0. So f inverse of 0 should give me 3. Okay, what about the next question? Actually, it's very similar, right? I want to solve f of x equals 0. So what is the x for which the output is equal to 0? Well, again, the output is 0 when the input is 3. So in this case, x is going to be equal to 3. Okay, because we know that f of 3, right, f of 3 gives me back 0. And then finally the last one, I want to solve f inverse of x equals 0 for x. So what must x be such that if I take the inverse of it, I get back 0? So think of it as, right, I want the inverse of an output that gives me back the input of 0. Well, when the input is 0, the output is 2, right? So if I do f inverse of 2, that gives me back 0, right? That's the same thing as saying f of 0 should give me 2. So f inverse of 2 should give me 0. So in this case, x is equal to 2. Okay, now, because the inputs and outputs switch, that means the domain and range of the inverse function and the regular function are also going to switch. So we can say that, let me say domain and range of inverse functions so the range of a function f of x is the domain of the inverse function f inverse of x. And vice versa, the domain of f of x is the range of f inverse of x. So, for example, let's say I gave you this function. We won't get into exponential functions until much later. If we have time, we'll do it at the very end of the course. But let's say we have this function which is e to the x, right? It turns out that the domain and range of this function are the following. The domain is all real numbers, so negative infinity to infinity. And the range is from 0, but not including 0, all the way to infinity. And then if I tell you that, let's say it has an inverse. So let's say this is the inverse. Actually, let me call it something different. Let me call it g. So g is the inverse. And it turns out the inverse is what's called the natural log function. So ln of x. So the question is, what is the domain and range of that natural log function? Well, without even having to know anything about exponential functions and log functions, we know that if one function is the inverse of the other, then the domain and range are going to switch, right? So the domain must be what the original range was. So domain of the log is 0 to infinity. And then the range is going to be the original domain, so it's negative infinity to infinity. Okay? So the domain of the original function switches, it becomes the range of the inverse function. And vice versa, right? So the domain switches and the range switch. Okay, next topic is how do we actually find equations for inverse functions? Right? Given, if we're given some original function, how do we find the inverse function if it exists? So finding the inverses of functions represented by formulas. Okay, so let's say we're given some function, say f of x is equal to 6x plus 14. It turns out this is a one-to-one function, so we want to find its inverse, f inverse of x. Okay, so there's several steps to do this. First of all, instead of calling f of x, give it a new name. Like call it, typically people use y. So I'll say rename f of x to y. So it's just easier to use y. So y equals 6x plus 14. And now what we do is we solve for x. So solve that equation for x. Okay, so how do I do that? Well, I would have to bring the 14, right? Subtract 14 from the right-hand side. Whatever I do to one side, do the other side. So I have y minus 14 is equal to 6x. And then finally, divide both sides by 6. I'm going to write my answer on the left-hand side. So now I have x is equal to y minus 14 over 6. And now what you do is you switch the x and y variables. So literally, the x becomes a y, the y becomes an x. So now this is y is equal to x minus 14 over 6. And that new y is your inverse. So we can say now that the f inverse of x is equal to x minus 14 over 6. Okay, we could check it, right? So remember, one way of checking it is the following. If I compute f of f inverse of x, I had better get back x. And same thing if I do f inverse of f of x, I had better get back x. So let's check it. So f of f inverse. Well, in this case, right, remember the original function f was 6x plus 14. So where I have an x, I have to put in f inverse. Well, we found f inverse is x minus 14 over 6 plus 14. So you can see here that the 6's are going to cancel, right? These will cancel. And I have x minus 14 plus 14. Well, that's just equal to x. So that checks. And then let me check the other way. So if I do f inverse of f of x, if I form that composition, so now it's going to be x minus 14 over 6 is my outside function, but I have to put in the original function for x. So this is going to be 6x plus 14. That's like my x, right, for my inverse function. And then minus 14 over 6. Well, this is really just equal to 6x, right? The 14's cancel over 6, and then the 6's cancel, and that's also equal to x. So we did get the correct inverse function. All right, let's do another one. Given f of x equals 4x minus 3 over 3x plus 5, we want to find the inverse function. Okay, so rename f of x y. So I'm going to call this y is equal to 4x minus 3 over 3x plus 5. Now I need to solve that equation for x, right? I want to solve this for x. Okay, how do I do that? Well, since I have fractions, I probably want to clear out the fractions by multiplying both sides by the lowest common denominator, which in this case is 3x plus 5, right? So if I multiply both sides, the left-hand side by 3x plus 5, and the right-hand side by 3x plus 5. So right-hand side, these cancel, right? Left-hand side, I can distribute the y. So I have 3xy plus 5y is equal to 4x minus 3. Now remember, the whole goal is to solve for x, right? So I need to get the x terms together. So I guess what I can do, I'll do a couple things at once. I will subtract 4x on both sides. And I'll subtract 5y to get rid of that 5y from both sides. Okay, so now I have 3xy, right, 3xy minus 4x on the left-hand side. And the right-hand side, I'm going to have negative 5y minus 3. I can factor out an x, right? It's common to both terms, so I can pull an x out front. I'm left with 3y minus 4. And then finally, I can divide both sides by 3y minus 4. So this cancels again. And now I have x is equal to negative 5y minus 3 over 3y minus 4. Here's where we switch variables, so the x becomes y and the y's become x's. And that new y is my inverse now, so this is just another way of saying is f inverse of x is negative 5x minus 3 over 3x minus 4. Okay, now remember, you can only find an inverse function if the original function is 1 to 1. So sometimes the original function is not a 1-to-1 function, but you can restrict the domain so that it becomes a 1-to-1 function, and then it will have an inverse. So let me give an example of that. So let me write that first. So sometimes the domain of a function has to be restricted so that it is 1-to-1, so it becomes 1-to-1 and has an inverse. All right, so for example, let's look at the quadratic function. So I'll say, find the inverse function of f of x equals x squared. Right, so it's our toolkit function, it's a quadratic function. Okay, so I graphed our our typical quadratic function, right, our usual quadratic function, and notice that it is not 1-to-1, right? Why isn't this 1-to-1? Because it fails the horizontal line test, right? A horizontal line will pass through more than one point in the graph. Okay, so this is, first of all, let me write x, this is f of x equals x squared, and it's not 1-to-1. So as it stands, it doesn't have an inverse. But what if I just restrict the domain? So right now the domain is from negative infinity to positive infinity. What if I restrict, I did it in the second graph here, the domain to be from just 0, including 0, to infinity. So now if you look at this, it's a function still, right? It passes the vertical line test, and it's also a 1-to-1 function because it passes the horizontal line test. So therefore that function, the restricted function, will have an inverse. Okay, so now actually we can find the inverse. So we'll start with f of x equals x squared. Remember, just rewrite the f of x, rename it, call it y is x squared. Now I need to solve for x, right? Let me write it this way. So how do I solve for x? Well, to get x by itself, I need to take the square root, both sides. But remember, the square root could be positive or negative. So the question is, which one do I choose? And that depends on how I restricted my domain. So if I want, and if you look, I'm in the first quadrant, right? So if the x is positive, I also want my y to be positive. So it must be, in this case, the plus. Right, so I can just call this radical y. Now you switch variables. So x becomes y and y becomes x. And that new y is your inverse. Okay, let me give you a graph of that. Okay, so here's my graph of the original function. So this is f of x equals x squared, the one that's in blue. The green is the square root, so this should be the inverse square root of x. Now notice a couple of things. First of all, if I plot that red dashed line, this is just the identity function, y equals x. Notice that the original function, so the x squared function, and the square root, the inverse function, they're symmetrical about that line y equals x. And that's going to be true for any function and its inverse. They're going to always be symmetrical about that line y equals x. Okay, a couple other things that are interesting. Let's just look at a couple of points here. Let's say I look at, for my original function, right, if the input were 2, the output is 4. Okay, so I have this point right here, 2, 4. Now on the inverse function, if my input were 4, the output should be 2, right? Because it should flip. So this is like saying f of 2 is equal to 4. Then over here, I'm saying, well, if my input is 4 to the inverse function, my output should be 2, and it is. Right, because this is the point 4, 2. So this is saying f inverse of 4 gives me back 2. So we can see that the coordinates of the points flip-flop, right? And you can do that with other points as well. Those were just really easy to read off. So for example, whatever this is, let's say it's like 1.75, right? The output is 3. So then if I put 3 into my inverse function, I better get out around 1.75, and that's what I get here. Okay, so the inputs become the outputs become the inputs. And again, this only worked in this case because we restricted the domain of the original function, right? So we made it one-to-one so that we could find its inverse. Okay, let's do another problem where we find the inverse. Let's say we let f of x equal 6 plus square root of 2x minus 4. And we want to find the inverse of that. Okay, so I'll start by renaming f of x. I'll call it y. And then I want to solve this for x, right? So I need to, let me bring the 6 over to the left-hand side. So I need to subtract it from both sides. So I have y minus 6 is equal to the square root of 2x minus 4. And I'll put the square root on the left-hand side. And now how do I undo the square root? I need to square both sides. So this is going to be 2x minus 4 equals. Now remember what y minus 6 squared means, right? It means y minus 6 times itself. Okay, so you need to FOIL that out. You need to multiply this out. So this is going to be y squared minus 6y minus another 6y plus 36. Or I can write it as y squared minus 12y plus 36. So this is y squared minus 12y plus 36. So a few more things. Now I need to, remember, my whole goal is to solve for x, right? So now I need to add 4 to both sides. So I have 2x is equal to y squared minus 12y. 36 plus 4 is going to be 40. And then finally divide both sides by 2. So I'm going to get x is equal to y squared minus 12y plus 40 all divided by 2. And now we switch the names, right, the variables. The x becomes y and the y becomes x. And that is our inverse. Okay, here, let me graph this for you to show you this. Okay, so notice here that this was my original function, right, f of x. So that was the 6 plus square root of 2x minus 4. And then the blue graph was my inverse. And the inverse, remember, we just figured out was x squared minus 12x plus 40 all over 2. And that's the blue graph here. And I also had to restrict it, right? Because normally that graph looked like a parabola like this, right? It went down, and then I have this side as well. But then the inverse wouldn't be 1-to-1. So I restricted it so the domain was just from 6 to infinity. And that made it 1-to-1. Okay, and notice here that both graphs are symmetrical about this line again, y equals x. And again, that will always be the case. If you plot the original function, the inverse function, its graph will be symmetrical about that line, y equals x. So if we find some points, you know, like in the original function, let's say, I don't know, it looks like this point is pretty close right here. So if the input is 14, the output is 11. So in the inverse function, if my input is 11, the output should be 14. Right? It's off just a little bit because that wasn't exact. But again, the inputs and outputs flip, right? They switch. They switch their roles. Okay, here's another example. Let f of x equal x squared, or sorry, x minus 5 squared. And we want to find a domain on which f is 1-to-1 let's say we also want it non-decreasing. And then once we find that, right, we make it 1-to-1, then we want to find the inverse of f restricted to that domain. Okay, so what is this function? Well, it's basically a quadratic function that is shifted, right? In fact, it's going to be shifted to the right by 5 units. Now, this is when Desmos is your friend, right? It's always nice to graph these things and figure out what's going on. So let me plot this, and then we'll figure out a restricted domain to make it one-to-one. Okay, so here's the original function, right? So this is the function x minus 5 squared. And notice it's not one-to-one, right? Because it fails the horizontal line test. So what can we do? Well, we want to restrict it so that it's one-to-one, and in this case, we want it to be non-decreasing. So it's obviously decreasing here, and it's increasing here. It has a minimum. In this case, it's a relative min and an absolute min, right here at 5, 0. So we just want 5 on, right? We want our domain to be 5, including 5, to infinity. Then we'll only include this non-decreasing piece. Okay, so we're going to restrict our domain to 5, infinity, including the 5. And that gives us the second graph, right? So now, let me write the fact that we restricted. So we restricted the domain to 5, infinity. Where originally, the original domain was negative infinity to infinity, but the function was not one-to-one. But by restricting it, we made it a one-to-one function, right? In this case, it passes the horizontal line test, so it's one-to-one. Okay, so let's find the inverse, and then we'll plot everything out again. So remember my original function was x minus 5 squared. So I'll make that y. Then I'm going to solve for x. I'm going to write this term on the left-hand side. And I need to take the square root, right, on both sides. So I'm going to have x minus 5 equals, and this is really plus or minus, but which one do I want? Well, if you think about it, again, because of the way I restricted the domain and chose just the increasing piece, I want the positive square root. Right? I could have, if I wanted to, I could have chosen this piece, restricted the domain from negative infinity to 5, and just looked at this piece, but decided to use this piece. Right? Either one would have worked. But because I did that, that means here I have to take the plus root. Okay? Now I would add 5 to both sides. So I have x is equal to square root of y plus 5. And then remember, I switch variables. And now that new y is my inverse function. Okay, so here, let's plot that and let's make sure it makes sense. Okay, so here was my original function, in the green here. This was x minus 5 squared, although the domain is restricted, right? It's just from 5 to infinity. And then the inverse is going to be the one that's in purple. So this purple graph is the square root of x plus 5. And notice that, right, the function and its inverse are symmetrical, again, about that line y equals x. Right? Symmetry about that line. Okay, let's do one more example, and then that'll be it for inverse functions. That'll be all I want to talk about for inverse functions. So last example. Let's say we're given f of x is equal to negative 2x to the 5th minus 8. and we want to find the inverse function. Okay, so same process as before, right? Rename the f of x, I'll call it y. And then I want to solve this equation for x. So I need to add 8. Now what I'm going to do is I'm going to rewrite the x term on the left-hand side and then write the y plus 8 on the right-hand side. I would have to divide by -2. So this is going to be x to the 5th equals y plus 8 divided by -2. And then and you could also put the negative in the numerator if you wanted to. And then how do I get x? If I have x to the 5th, I need to take the 5th root, right? You take the 5th root of both sides. So in that case, I'm going to have x is equal to the 5th root of y plus 8 over -2. And then finally, you can switch variables. So this is y is equal to the 5th root of x plus 8 over -2. And that should be my inverse. Okay, let me plot these. So that should be the inverse. And let's make sure that this is the case. Okay, so here is the graph. So in this case, the original function, so the -2x to the 5th minus 8, that's the green function. So the green here is f of x. Oops. The green is f of x equals -2x to the 5th minus 8, right? It looks like an x to the 5th function because it gets really flat here. It's negative, right? So it's flipped and it's shifted down by 8. Right? So that's the original function. And then the inverse that we found was the blue function. So we found that the inverse function was the 5th root of x plus 8 over -2. By the way, you could also write it like this, right? You could say it's x plus 8 over -2. And remember, 5th root is the same as raising it to the 1/5. Right? So the 1/5 becomes my exponent. Okay, so that's the blue. And notice that, again, they are symmetrical as they should be. Symmetrical about that line. This is the line y equals x. So this is just the line y equals x. So the input to one function becomes an output, and the output becomes the input to the inverse function, right? So again, the roles flip. Okay, that's all I want to talk about in terms of inverse functions. And actually, that's it for chapter 3. So the next lecture, we will begin talking about chapter 4 on linear functions. Now, we've already talked a little bit about linear functions, but we'll get into more details on linear functions. Thanks.